So good morning again. We're gonna delve into Newton's laws in a little bit more detail. Newton, um, the English physicist, had three laws, and we are going to discuss the first law in a little bit more detail, so you'll understand what Newton was getting at. So Newton's first law of motion is also referred to as the law of inertia. Um, So what he's saying that if you have an object, so remember you have to relate these things to everyday activity because physics is a study of everyday activity, studying the physical environment. So if you have an object at rest, so you have your book on your table, your book on your table is gonna stay there, okay, unless it is acted on by some force. If you throw your book on the table and it was sliding on the table, that book will slide on the table if it's moving at a constant velocity. It will slide on that table continuously, never stopping, if there were no friction, unless it is acted upon by some force. Okay? So that's what Newton was saying. So if you eliminate friction, an object that is moving will continue to move at the same speed, constant speed, and in the same direction unless it is acted upon by an outside force or an unbalanced force. So we're going to discuss unbalanced force in some details. So what he's saying, an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So we'll discuss what an unbalanced force is because you have to understand that thoroughly. So in essence, objects keep on doing what they're doing unless they're acted upon by some external force. So if the book is on the table, it's going to stay on the table. Nothing is going to happen to it. If the book is sliding on the table, it's going to continue to slide on the table with a constant velocity unless it is acted upon um, by an external force. It's going to continue with that same speed and in the same direction unless it is acted upon by an external force, an unbalanced force. So we gave this example, the soccer ball uh, is at rest and the soccer field. So it's an object at rest and it will stay there unless an unbalanced force move it. So if someone kicks the ball, that's an unbalanced force. It's an external force, and then the ball will continue to move same speed, same direction. If there were no resistance, just think about if there were no resistance, the ball will continue to move in the same direction and with the same speed. And it will do so unless it is acted upon by an unbalanced force. So the net is an unbalanced force which prevents it from going further. Uh, um, so that basically saying the same thing when if you have a rocket going up, you say you send a rocket up, you have to produce some force to send the rocket up. That force that you producing to send the rocket up has to be greater than the weight of the rocket, so it's not going to move. So the difference between the two force is what we call the net force. and the net force is upwards. So the rocket will move upward. And we went into the definition of inertia and mass. So that inertia is a tendency of an object to resist change in its state of motion. And in essence, it's the resistance an object has to change in its state of motion. And inertia and mass is the same thing. You know, if an object have a large inertia, it's going to have a large mass. Okay, so and it's going to take more force to change its direction. So think of inertia and mass as the same thing. Okay, inertia and mass is not; these are not quantities that are going to change. Inertia and mass, these are fixed quantities. So on Earth, the mass or inertia is going to be of a certain value. And say Mars, mass and inertia is going to be the same thing. The weight is going to be different. Okay, but the mass or the inertia. So again, Galileo was one of the earlier scientists to discuss motion. And Galileo said moving objects stop because of a force called friction, which is essentially correct. Without friction, an object will continue to move in the same direction and at the same speed. And he said that a force is not needed to keep an object in motion, Newton said that. So Newton says that a force is not needed to keep an object in motion if you can eliminate friction. If you eliminate friction, the object will move in the same direction, same speed. Okay. So when we say mass, again, mass is a measure of the inertia. Okay, the resistance to change in motion. Okay, and so they're sort of interchangeable property of an object. All right. So how can we apply Newton's first law of motion to everyday activity? Remember, when we talk about physics, we have to relate it to everyday activity. If you can't do that, then it's not relevant. So, say for instance, you're driving in a car. If you're driving in a car and the car is moving at a certain speed and in a certain direction, okay, so the car and yourself, because you're sitting in the seat and the car is moving, is going to move you at the same speed and in the same direction. If the car strikes a wall, okay, then that unbalanced force is going to cause the car to stop. The car will decelerate abruptly because of the unbalanced force of the wall. If you are, you're gonna continue to move with the same speed and in the same direction unless an unbalanced force stop you. You're driving the car. So if you're not restrained, you're gonna continue to move forward, and you will be ejected from the car, and you'll sustain severe bodily injury. So if you have a seat belt, so a seat belt is an unbalanced force that will prevent you from moving at the same speed and in the same direction. Okay? So again, you're driving the car, in a certain direction, certain speed, you hit a wall. The wall will stop the car because the wall is the unbalanced force. It's going to stop the car. But you're going to continue to move in the same direction and at the same speed. You will be ejected from the car unless you have a seat belt. So the seat belt would be an unbalanced force. Okay? If not, you'll be projected. You'll be ejected from the car, and you become a projectile. So that is the rationale for seatbelts. So seatbelts weren't constructed because of whatever. Seatbelt is an unbalanced force which will prevent you from ejected from a moving vehicle. Okay, so just think about it. You're driving in the car, you're moving at the same speed and in the same direction as the car. If something stopped the car, it didn't stop you. So everything in the car will move with the same speed and in the same direction unless some unbalanced force prevents it from moving. So that is why you need a seatbelt. Okay? Again, Galileo states that a force is needed to keep an object in motion. And we know that that's not really correct. Okay? You don't need a force to keep an object in motion. So that was one of the deficiency of Galileo's uh, law, if you want to call it that. So you don't need a force to keep an object in motion. Uh, but he correctly stated that objects stop because of friction. And Galileo did a few experiments, and this is one of Galileo's experiments. So he devised some incline. So he had an incline right here and a level surface, and then an incline going up. So incline going down and an incline going up. And he released a ball, and what he observed was that the ball slid down the incline, and then when it went up this side of the incline, it went up the same height, vertical height, as when it started. Okay, so it went up the same height. um, so that was one of his first experiments. Again, at, objects will travel. Objects will travel at the same height. Okay, objects will travel at the same height if it is released uh, from an incline. And again, if this inclination is the same as this inclination, then to travel at this, it's going to travel the same height. If this inclination is different, okay. So when we say inclination, this angle to horizontal is the same as this angle. It's going to go it's going to travel up this side the same height. All right. So you release in this second example. Okay, this inclination is different. So this is steeper than over here. So you release the ball, okay, and it come down the incline, travel on the horizontal. It's going to move up the same height again, move up the same height. What you'll observe is that it's going to travel a longer distance, however. It's going to travel a longer distance to reach the same height because this incline is less than this one. The angle over here is less than the angle over here. But the object needs to achieve the same height, so it will travel a longer distance. See, a longer distance this way to achieve the same height, vertical height. In this experiment, okay, certain inclination, you release the ball, it's at a certain height from the vertical, but this is horizontal. It is horizontal. What Galileo postulated was that the object will travel continuously. The object will travel continuously unless, I mean, unless you have some force, and possibly that force is friction. Okay? this object is trying to do is trying to achieve the height at which it started. So it's going to travel continuously trying to get to the height it started at. Okay, so this was another of Galileo's experiment, uh, looking at motion. Okay, let's get back to Newton now. So Newton stated that a force is not needed to keep an object in motion. An object at rest will remain at rest, and an object in motion will continue in motion at the same speed and in the same direction unless it is acted upon by an unbalanced force. um, so this is Newton's second law, and we'll go into it, but I'll just point it out right now. Newton's second law states that a force is equal to mass times acceleration. Newton's second law states that force is equal to the mass of an object times the acceleration of that object. If the object is not accelerating, then there is no force acting on that object, or no unbalanced force then. Okay? So if there is no acceleration, then there is no force. Remember what we said, when an object is moving, if it's moving at a constant velocity in a certain direction, remember from earlier lecture, acceleration is a change in velocity. So if you have constant velocity, there is no change in acceleration. Hence, there is the force which is equal to mass times acceleration is equal to the mass times zero. So there is no force. No force. Okay? So again, we'll look into this in a little bit more depth, but Newton states that force is equal to the mass of an object times the acceleration of that object. Okay? Or the acceleration that the object is subjected to. Okay, if you have something or an object which is moving at a constant velocity, something moving at a constant velocity, it's not accelerating at all. There is no acceleration. So force which is equal to mass times acceleration is equal to mass times zero. So no force is acting on that object. So an object which is moving at a constant velocity, there is no force, no unbalanced force that's acting on that object. So Newton states that a force is required to stop a moving object. Okay? Just like when you're driving your car and you hit a wall, a force, that unbalanced force, is required to stop that moving object. And if you're not belted in the car, you're going to become a projectile and you're going to be ejected from the vehicle. If you have a seat belt, then that unbalanced force will prevent you from becoming a projectile. So Newton states that a force is required to stop a moving object, and it is called friction. But without friction, the object will move same speed, same direction, okay? And because the velocity is constant, there is no acceleration, no force, no unbalanced force. Again, if you slide a book on a tabletop, it will continue to move forever if there were no friction. Okay, so we're gonna look at a new concept. Okay, so this is a book. The book is on the table, and we know that gravity is going to pull the book downwards. Okay, weight is actually a force. So that's a difference between mass and weight. Weight is a force. So the weight of the book, remember what we said, Newton's second law, even though we're not there yet. Newton's second law states that the force is equal to the mass times the acceleration. So the weight of this book, which is the force pulling it downward, is equal to the mass of the book times the acceleration. And because it's the acceleration is acceleration of gravity, then we multiply the mass of the book times acceleration of gravity, and that is the weight or the force that that the gravity is pulling downward on the book. So gravity is going to pull downward on the book because of 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 the force that's pulling the book downwards. Okay, so again, force is equal to the mass of the book times the acceleration of the book. The acceleration is the acceleration of gravity. Okay, the book is on the tabletop, and because the book is not going into the center of the earth, the book is stationary. The book is not moving. The tabletop have to push up on the book the same force as the book is pulling downwards, as the gravity is pulling the book downwards. So when you have a stable surface which supports an object, the weight of the object, which is the force pulling it downward, is going to be balanced by the stable surface, which is pushing upward on the object. So these two forces are balanced. So when you have an object at rest, it is telling you that the downward force due to gravity, is equal to the upward force, okay? Because it's not moving. So these two forces have to be the same for it not to be moving. So this is what we call a balance force. This is a balance force. The force pulling the book downward, which is force due to gravity, and then the surface, which holds the object or the book, prevent it from dropping to the center of the earth. It holds it upwards. So this is the force of the table pushing the book upwards. Okay, stable. So this is unbalanced. This is balance force. So balance force is the forces. The forces are equal in magnitude and opposite in direction because the object is not moving. Object is not moving. So the force have to be the same but in the opposite direction to prevent a stable object from moving. And we usually represent these scenarios with what we call free body diagrams. So when we describe a motion, we can use free body diagrams to fully describe these motions, and I'll explain further. Again, balance force. If you are standing on a surface, say you're standing on the floor in your living room, your weight, which is the force due to gravity pulling you downwards, so that force pulling you downward is equal to your mass times the acceleration due to gravity, okay? That is the force pulling you downwards. Force pulling you downwards is your weight. Remember, weight is a force. Force is equal to the mass of an object times the acceleration. So whatever mass you have, you're going to multiply it by g, acceleration due to gravity. And then the floor is going to push upwards. The floor is going to push upwards the same amount as your weight, but in the opposite direction. Okay? Your weight is downward, the force is going to push on you upwards. If these forces weren't the same, you'll be either moving up or down. So this is what we call balance force, or balance forces. Same thing over here. If you have an object say a cinder block, and you have 2 newtons. So force, we usually, the unit of force is the newton. Again, force is equal to the mass times acceleration. Mass is in kilograms. Acceleration is in meters per second squared. And that is what we call the newton. So a newton is kilogram, which is the mass, and then the acceleration, meters per second squared. So if you have 2 newtons pulling the cinder block up, 2 newtons pulling it downward, 5 newton pulling it to the right, and 5 newton pulling it to the left. So these are balanced forces. The upward force is balanced by the downward force. The force to the right is balanced by the force to the left. So this block is not going anywhere because the forces are balanced. Forces are balanced. So the block will be stationary, not moving. So those are examples of unbalanced forces. So when the forces are unbalanced, that means there's a difference in the forces. The forces acting on an object are not the same. When you have an unbalanced force, so when you have a force, again, force is equal to the mass of the object times the acceleration of the object. So the fact that if you have an unbalanced force, that object is going to be accelerating. So whenever you have an unbalanced force, the object is going to be accelerating. Unbalanced force causes acceleration. Again, remember, if you're standing in your living room, the downward force is going to equal to the upward force. You're not going to be going anywhere. However, if something hit you and you went up, that is the unbalanced force. Okay? And you're going to accelerate because force is equal to the mass of an object times the acceleration of an object. So unbalanced forces determine what forces are acting on an object and in what direction. So let's look at these scenarios. So if you have 5 newton of force pulling an object to the right and 5 newton of force pulling an object to the left, these are balanced force. So there's no motion, there's no net force, there's no unbalanced force. You need unbalanced force to give rise to acceleration. In this scenario, where you have 10 newton of force pulling to the right and 5 newton of force pulling to the left, there's a net 5 newton of force pulling to the right, okay? Because the rightward force is greater than the leftward force. So there's a net 5 newton of force pulling or pushing this object to the right. So this object is going to achieve some acceleration because there's unbalanced force. And this unbalanced force, remember, force is equal to the mass times acceleration. So because there's an unbalanced force, the object has a mass, it's going to achieve a certain acceleration in this direction. Okay, similarly, if you're playing tug and war and you have 300 newtons to the right, 300 newtons to the left, I mean, you'll be stationary. There's not going to be any motion. However, if you have 300 newtons to the right, 400 newtons to the left, there's a difference of 100 newtons to the left. So the motion is going to be to the left. Okay, this is an unbalanced force. So because you have an unbalanced force, you're going to get motion and you're going to have acceleration because force is equal to mass times acceleration. Net force is equal to mass times acceleration. So this is when we talk about a body diagram, a free body diagram. This is what we're talking about. So we usually represent free body diagrams like this. So this is the object, and if something is, say, pulling or pushing the object in this direction, we draw an arrow, and then the head of the arrow shows the direction that the force is acting um, on. Whenever you have an object, and you're always going to have the weight of the object pulling downward, the weight is due to the force due to gravity, and then you're going to have what we call the normal force, which is a supporting force. Because if you're standing, say you're standing on the floor in your living room, your weight is going to be equal to your mass times acceleration. The force due to gravity is going to pull you upward. The floor is going to support you. So the floor is going to push upwards on you. And this is what we call the normal force. So the normal force is going to be upwards, and the force due to gravity is going to be downward. And then if someone is pushing you or pulling you, that's what we call the applied force. And it's going to be in the direction. And then whenever you have motion, you're going to have friction, even though when we discuss Newton's first law, we say eliminate friction. But friction is a reality, and you have to deal with friction. So friction is going to be in the opposite direction to the direction of motion. Okay? So friction is going to be in the opposite direction to the applied force. So this is an example of what we call a free body diagram. Weight, or the force due to gravity, is downward. Normal force is going to be in the opposite direction. The normal force is always perpendicular to the surface that you're talking about. The normal force is always perpendicular to the surface. This is the applied force if someone pull you or push you, and then friction is in the opposite direction. Okay? So that's a free body diagram. This is just an exercise looking at balance and imbalance forces again. Okay, so in scenario one, if you have 60 newtons to the right, 10 newtons to the left, there's an unbalanced force of 50 newtons. And then this is balanced because you have 10 to the right, 10 to the left, so the object will be stationary. When you have unbalanced force, force is equal to mass times acceleration, you must have an acceleration. When you have unbalanced force, you must have acceleration. You're going to have motion then. Okay, in the third case, you have 50 to the left, 40 to the right. There's a difference of 10 to the left, so you have 10 newtons to the left. To find the acceleration, force is equal to mass times acceleration. You divide the force by the mass, and you'll find what acceleration to the left this object is achieving, and then similarly for the other ones. So you need unbalanced force for you to have a motion. Okay? So, when Newton talk about a force is a push or a pull. Just think about it. Force is a push or a pull. It's an interaction between two or more objects, and either they're being pulled or pushed. Um, and so when we discuss force, a force is either a contact force or a force at a distance. So if someone is pushing you, that is contact force. All right. Someone is pulling you, that is contact force. You have to be in contact with the object. Okay. So these are some examples of contact forces. You need physical contact between the object and the whatever is supplying the force. So friction, you're pushing the book on the table, The friction is going to be in the opposite direction to the motion of the book. So frictional force is a contact force. Tensional force, if you pull on uh, a string, if you pull on a string, then the force on either side, because you have contact, is a tensional force is contact force. Normal force, again, you're standing in your living room. The living room is pulling you. Sorry, the gravity is pulling you downwards. Force of gravity. The living room is pushing you upward. You're in contact. So normal force. So the normal force is when the floor push upwards, on you. So that's a contact force. Air resistance is another contact force. Applied force, someone pull you or push you. And then spring force, and we'll discuss spring force um, in more detail later. So those are contact forces. So you have to know the difference. Action at a distance force, you need no physical contact. No physical contact is needed for action at a distance uh, force. You're going to get a push or pull despite physical separation. You'll get a push or a pull despite not being in contact with the object. And action at a distance forces includes gravitational pull, because if you in a tree and you fell out of the tree, gravity is pulling you downward even though you're not in contact with anything. So that is so gravitational pull is action at a distant force. Electric force, because of the electric field that is generated, that also uh, action at a distant force. And magnetic force. So these are the three examples of action at a distant force. No physical contact is necessary. All right. Again, contact force. Okay. Gravity or the weight of the object is downward. Normal force is upwards. Once you're on a stable surface, you'll be supported by the stable surface. So that stable surface is going to push upwards on you. If the applied force is to the right, then the friction will oppose the motion, so it's going to be to the left. So these are the different force that will act on an object. If you have an applied force, you say you're pushing or pulling, and friction, the normal force is upwards. In this case, it's always perpendicular to the surface. The normal force is always perpendicular to the surface you're talking about. And then the weight is going to be downward. Again, if you have an object on an incline, okay, gravity is always straight down. Gravity is going to be vertical. Gravity is not going to be at any angle to anything. Gravity is going to be straight downward. Because this object is on an inclined surface, the normal force is going to be perpendicular to the surface. Okay? Friction is going to be in the opposite direction to the motion. So if this object is sliding down the surface, the friction is going to be upward. The weight or the force due to gravity is going to be perpendicular, down, straight, vertical. The normal force is that is, the surface is going to push upward on this object, and it's going to be perpendicular, 90 degrees to the surface. So this is a free body diagram of this object on an incline. Okay, again, if you push on an object, that's an applied force, that's a contact force. And then if you pull on a string, okay, this person is pulling, this person is pulling, there's a force that's going to pull this individual this way, and there's a force that's going to pull this individual that way. That's tensional force. Okay? So once there's no motion, the tension is going to be equal and opposite in direction. Okay? Again, if you have a crane, a cable, a ball, the weight of the ball is going to be downward. Tensional force is going to be upward in the strength. So that's a contact force. Again, you have an object, you have a pulley system, and there's a weight right there. There's going to be the weight of the object is going to be downward. Tension is going to be upward. Okay. Um, there's a tendency to try and pull this object this way, so the applied force will be this way. You're still going to have your weight or force due to gravity downwards, and then you're going to have the normal force upwards. So, and then spring force is another contact uh, force. So if you have an object on a spring system, if the object is pulling the spring system downwards. So the spring is gonna, so the spring is being pulled downwards, okay, by the weight of the object. So there's a tendency for the spring to be pulling upwards, okay. So not a contact force, okay. Contact force is the force acting. So you use your free body diagram to show the forces acting on an object. Okay, someone say skydiving, gravity pulls them down, force due to gravity. Air resistance is going to be upward. Air resistance is upward. Okay, as opposed to action at a distance force. So if this is the sun and this is a planet, of course, there's going to be a gravitational pull of the sun on the planet. So this is a gravitational pull. Okay, so there's no contact between those two planetary bodies. And again, electric force, okay, the electric field, there's no contact, so it's action at a distance force. Okay, so we're gonna stop here. You know, uh, again, when we talk about a force, we ventured into Newton's second law, which said that force is equal to mass times acceleration. And we mentioned that 1 Newton of force is required to move an object of mass 1 kilogram with an acceleration 1 meter per second, or 1 meter per second squared. So the Newton, the, the Newton, the unit Newton is equal to kilograms, which is the mass, times the acceleration, which is meters per second squared, or mass, or sorry, or meter per second per second. So the Newton is equal to kilogram per meters per second squared. Okay? So 1 Newton is equal to 1 kilogram per meter per second squared. Okay, same thing. All right. But when we will